Imagine, at the heart of a galaxy, a vast and invisible force that governs its very existence. This hidden power is none other than a supermassive black hole, and while they are often portrayed as chaotic, all-consuming monsters, these giants play a vital role in the life of a galaxy. At the center of most large galaxies, there lies a supermassive black hole. Their gravity is so powerful that not even light can escape. Yet, they do far more than just absorb matter. They are like the heart and lungs of a galaxy, breathing life into their cosmic environment in ways we are only just beginning to understand. Recent studies have shown that jets of gas and radiation erupting from the poles of supermassive black holes are similar to the air that sustains our lives. The shockwaves from these jets ripple like the diaphragm in our chests. The movement of the diaphragm makes our lungs expand and contract, and this respiratory system helps to regulate the growth of the galaxy, preventing it from becoming too large and ensuring the delicate balance of the cosmic ecosystem. A simulation shows how the galaxy's heart and lungs, the outflow of gas from the central supermassive black hole, can extend the galaxy's life. If these supermassive black holes didn't act as the galaxy's regulators, the cosmos would be filled with zombie galaxies, vast clusters of dead or dying stars. The shockwaves generated by the black hole's jets can suppress star formation by heating the surrounding gas, preventing it from cooling and condensing into new stars. This process, while seemingly destructive, is essential for maintaining the health and longevity of a galaxy. Tonight, we will journey to understand the mysterious nature of supermassive black holes and explore their profound impact on the universe. By the end, we will come to see that even in the darkest corners of the universe, there is a heartbeat that connects us all. To fully appreciate their influence on galaxies, we need to understand how they are formed, their different types, and some key discoveries. Black holes form in two primary ways, with the most common method being linked to the death of a massive star. When a star with about 8 to 10 times the mass of our Sun runs out of nuclear fuel, it explodes in a cataclysmic event called a supernova. The core of the star then collapses under its own gravity, forming a stellar mass black hole. These black holes typically have a mass a few times that of our Sunday. Another way is through the direct collapse of a massive gas cloud, a process that bypasses the star formation stage entirely. This can create black holes with masses ranging from thousands to hundreds of thousands of times that of our Sunday. It is believed that this direct collapse occurred in the early universe, planting the seeds for the supermassive black holes we see today. The concept of a black hole was first predicted by Carl Schwarzschild in 1915 as an exact solution to Einstein's equations of general relativity. These equations describe how matter warps the fabric of space-time, and Schwarzschild's solution revealed regions where gravity becomes so powerful that nothing, not even light, can escape. The first observationally confirmed black hole was Cygnus X1, discovered in 1964. This stellar mass black hole in our Milky Way galaxy was identified by the X-ray radiation produced as it accreted matter from a companion star. This discovery was the first strong evidence that black holes were not just theoretical constructs, but real objects in our universe. Scientists have since determined that a black hole consists of three main regions: the event horizon, the photon sphere, and the singularity. The event horizon is the point of no return. Once something crosses this boundary, it cannot escape. Within the event horizon lies the photon sphere, where gravity is so intense that particles of light are forced into orbit. At the very center is the singularity, a point of infinite density, where the laws of physics, as we know them, cease to apply. Black holes come in a range of different sizes. Stellar mass black holes, formed from collapsed stars, have masses a few times that of our Sunday, residing at the center of most galaxies. Are supermassive black holes, with masses ranging from millions to billions of times that of our Sunday. Less common are the intermediate mass black holes, which fall in between, with masses from 100 to 100,000 times that of our Sunday. In 2019, the Event Horizon Telescope collaboration captured the first ever image of the black hole at the center of the M87 galaxy. This landmark image shows the black hole's shadow cast against a glowing accretion disk. This observation provided direct visual evidence supporting our theories about black holes, opening up new possibilities for studying these enigmatic objects. One of the most common and debated questions about black holes today is whether they can die. According to Stephen Hawking's theory, black holes can slowly evaporate over immense timescales through a process known as Hawking radiation. This occurs when virtual particle pairs form near the event horizon. One particle falls into the black hole while the other escapes, and over an incredibly long time, this stream of escaping particles causes the black hole to lose mass and ultimately evaporate completely. While often portrayed in science fiction as cosmic vacuum cleaners, black holes don't indiscriminately pull in everything around them. For an object to be captured, it must venture very close to the event horizon. Furthermore, while some have suggested black holes could be wormholes or gateways to other universes, these ideas remain purely speculative, with no observational data to support them. Scientists estimate that our Milky Way galaxy alone contains over 100 million black holes. Understanding the fundamentals of black holes, including their formation, different types, and key discoveries, provides a solid foundation for exploring their profound influence on galaxies and the entire cosmos. So, while supermassive black holes themselves are invisible, their presence can be felt through the immense gravitational force they exert on their surroundings. But how do these colossal celestial bodies form, and what are their defining characteristics? In theory, when a massive amount of matter is compressed into an incredibly small space, it creates a gravitational field, so powerful that nothing can escape. This is the birth of a black hole. This concept, once deemed too fantastic to be real, is now an accepted scientific fact. Black holes, especially the supermassive variety, are scattered throughout the cosmos, potentially numbering in the billions, with masses millions, or billions of times that of our Sun. These supermassive black holes are detected through their gravitational effect on nearby stars. These stars orbit the black hole at speeds much greater than they would orbit a regular object of comparable mass, and by measuring these orbital velocities, astronomers can calculate the black hole's mass. For instance, Sagittarius A asterisk at the center of our own Milky Way has a mass of about 4 million times that of our Sunday. Some supermassive black holes dwarf even Sagittarius A asterisk. In the dwarf galaxy Leo I, there's a black hole with a mass of about 3 million solar masses, and in the nearby elliptical galaxy Centaurus A, there's one with a staggering mass of 55 million solar masses. Even more immense, a black hole in the galaxy cluster Abell 2261 is estimated to have a mass of around 100 billion solar masses, though its precise location remains unconfirmed. These black holes, particularly those in active galaxies, exhibit a variety of behaviors. Surrounded by an accretion disk of rapidly swirling gas and dust, they can release tremendous amounts of energy, sometimes outshining their entire host galaxy. This process was brilliantly captured in 2019 by the Event Horizon Telescope, which imaged the accretion disk around the supermassive black hole in galaxy M87, revealing the haunting shadow of an object. With 6.5 billion times the mass of our Sunday, the formation of these supermassive black holes is a topic of intense research and speculation. Unlike the vacuum cleaners of sci-fi, real black holes attract matter via gravity rather than actively sucking it in. This gravitational pull is incredibly powerful at close range, but from a distance, it behaves just like the gravity of any other object of similar mass. According to one theory, the most ancient supermassive black holes formed almost instantaneously when massive gas clouds containing millions of solar masses collapsed under their own gravity. This direct collapse model suggests that such a black hole could form in as little as 150 million years, which is just a blink of an eye on the cosmic timescale. Another hypothesis suggests that under the extreme conditions of the Big Bang, primordial black holes were born, serving as seeds for later growth. By studying these colossal objects, we gain profound insights into the fundamental processes that shape galaxies and, in turn, the universe itself. But what happens when two galaxies collide? It's not just a dramatic cosmic spectacle, it is a process that reshapes the fabric of the universe. And at the heart of these galactic collisions are their supermassive black holes. Their interactions create some of the most powerful phenomena known to exist. As the galaxies approach one another, the supermassive black holes at their centers begin to interact gravitationally, spiraling closer together toward an inevitable merger. This process is far from silent. Sweeps up vast amounts of surrounding gas and dust, creating a turbulent environment that sets the stage for all sorts of extraordinary phenomena. Physicists have simulated these massive merger processes and found that as black holes spiral toward each other, they can generate extremely powerful electromagnetic radiation jets, which are ejected along their axis of rotation. These are far more powerful than the jets typically observed around isolated black holes. This cosmic performance begins long before the black holes fully merge. This provides a potential early warning for these events. When these supermassive black holes finally merge, their jets will combine into a single high-energy burst, which may be accompanied by less directional bursts, increasing the chances of detection. The merger process sets the surrounding plasma in motion, generating powerful jets. In theory, these jets can be observed from billions of light-years away. Detecting these cosmic events is not only exciting, but also offers a unique opportunity to test the limits of Einstein's theory of general relativity under extreme conditions. Observations of these mergers will either strengthen our current understanding of gravity or open up new realms of physics, potentially leading to alternative theories. Future missions, like the Laser Interferometer Space Antenna, are expected to expand our ability to locate these mergers. It's a joint project between NASA and the European Space Agency. It will orbit the Sun, detecting the gravitational waves produced by these merger events. Combining gravitational wave data with electromagnetic observations will allow for precise localization and detailed study of these high-energy events. But before these advanced instruments are operational, astronomers rely on existing observatories to detect the electromagnetic jets. These jets provide a dynamic perspective on galaxy evolution, showing how such mergers can significantly alter a galaxy's structure and behavior. Let's take a closer look at Sagittarius A*. Its mass is 4.3 million times that of our Sunday this past mid-spring. With advanced observations from the Event Horizon Telescope, this giant in our galaxy has revealed new secrets. For the first time, astronomers have recorded polarized light from around Sagittarius A*, which gives us insight into the magnetic field surrounding this black hole, offering a new perspective. Polarized light is crucial for understanding these magnetic fields because it reveals the orientation of light waves, allowing us to learn about the properties of the gas and the mechanisms that power the black hole. Interestingly, the magnetic field around Sagittarius A is remarkably similar to the one observed around the much more massive black hole in the galaxy M87. The black hole in M87 has a mass 6.5 billion times that of the Sunday. This similarity suggests that strong, ordered magnetic fields may be a common feature of all black holes, regardless of their size. The presence of this magnetic field has led to speculation that Sagittarius A might be hiding a jet. In other black holes, these magnetic fields drive powerful streams of matter. Although Sagittarius A appears relatively calm and consumes little material, the similar structure of its magnetic field suggests the possible existence of a faint, as yet unobserved jet. This new image of the black hole at the center of the Milky Way tells us that strong swirls and ordered magnetic fields exist near it. The co-leader of the study, a recipient of NASA's Hubble Fellowship Program and an Einstein Fellow at the Harvard and Smithsonian Center for Astrophysics, Sarah Issoun, said, "These magnetic fields are crucial for how black holes interact with the gas and matter around them. It is precisely the Event Horizon Telescope, an array of telescopes from around the world, that made these groundbreaking observations possible." By combining data from multiple telescopes, the EHT forms a virtual telescope the size of Earth, capable of capturing unprecedented detail of black holes. Although Sagittarius A is closer to us, its smaller size means the material orbiting it moves very quickly, making it difficult to get a clear image. In contrast, in the much larger M87, the material moves more slowly, making it easier to observe. Overcoming these challenges has provided invaluable data for comparing black holes at both ends of the mass spectrum. The similarity between the observed magnetic fields of Sagittarius A times and the M87 black hole suggests that if our galaxy's central black hole does have a hidden jet, it would offer new insights into the behavior and evolution of black holes and their host galaxies. The observation of such a jet would be a major discovery, linking Sagittarius A* to the high-energy processes that shape galaxies. Discovering such a jet would greatly expand our understanding of how black holes influence their surroundings. Jets can expel gas and dust, influencing star formation and the overall evolution of a galaxy. By comparing different black holes, astronomers will be able to determine the universal laws that govern these mysterious objects. Studying our own supermassive black hole allows us to connect these abstract concepts to a familiar environment, making the distant universe feel a little closer. The influence of supermassive black holes extends far beyond their gravitational pull. Relativistic jets have a tremendous impact on the formation and evolution of galaxies, affecting everything from star formation to the distribution of gas and dust. A prominent example is the Teacup Galaxy, located about 1.3 billion light-years from Earth. The Teacup Galaxy gets its name from its unique handle-like structure, a feature formed by the relativistic jet activity of the supermassive black hole at its center. This galaxy vividly demonstrates how even low-energy jets can have a significant impact on their environment. Even in radio-quiet galaxies, jets can redistribute and disturb the surrounding gas, which affects the galaxy's ability to form new stars. Recent observations using the Atacama Large Millimeter divided by Submillimeter Array have shown that the jets in the Teacup Galaxy, though relatively weak, are capable of moving, heating, and accelerating the gas within the galaxy. Even in radio-quiet galaxies, jets can redistribute and disturb the surrounding gas, which affects the galaxy's ability to form new stars, says an astronomer from the Canary Islands Institute of Astrophysics. Cristina Ramos Almeida explains, the impact of these jets is not always direct. Studies have found that the most significant impact in the Teacup Galaxy occurs perpendicular to the direction of the jets. This lateral outflow is caused by shock waves from the jet-inflated bubbles. The shock waves heat and expand the gas, and these interactions can suppress star formation by preventing gas from cooling and collapsing into new stars, while powerful jets can heat the gas in a galaxy to a point that slows its growth and prevents new stars from forming. Weaker jets, like those in radio-quiet galaxies, also play an important role. These jets can still stir up the gas in a galaxy, setting it in motion and redistributing it. This activity can lead to the formation of new structures within the galaxy and influence its long-term evolution. Understanding the impact of these jets helps astronomers piece together the complex puzzle of galaxy formation. Supermassive black holes are an integral part of a galaxy's life cycle. From the dramatic changes caused by powerful jets to the more subtle but equally important effects produced by weaker jets. Stay with us as we continue to explore the forces that shape our universe. Our universe holds a mystery that has long captivated the human mind, a question that bridges the gap between the known and the unknown, the simple and the complex. Here on Earth, life thrives in a constant dance between order and chaos. Every life form is a testament to a hidden order, a pattern woven into the fabric of existence, from the smallest microbe to the largest mammal. But what if the complexity of life, the very essence of our existence, could be explained not just through the lens of biology, but through a mathematical framework? This is the domain of assembly theory. It is a groundbreaking concept that transcends traditional science, a journey into a world where mathematics and biology merge to reveal the hidden architecture of life. Imagine a universe where, from the simplest molecule to the most complex organism, the secret of life is encoded in the language of mathematics, waiting to be deciphered. In this universe, the line between life and non-life blurs, giving rise to new possibilities and new understanding. Let's explore together how this revolutionary idea is changing our perception of life, evolution, and the universe itself. Perhaps we can even get closer to answering the ultimate question: what is the true nature of life in the universe? Since the dawn of civilization, mathematics has been the language of the cosmos, is a tool for decoding the mysteries of nature. But this language, composed of numbers and equations, what does it have to do with understanding the essence of life? The core of assembly theory offers a simple yet profound idea. The complexity of life can be measured and understood through the lens of mathematics. Imagine life as a puzzle, where each piece represents a molecular building block. Assembly theory seeks to show how these puzzle pieces come together, step by step, to form the intricate structures that define living organisms. Each step in this assembly process represents a leap in complexity, from simple atoms to complex proteins. The theory introduces the concept of the assembly index, which is the cornerstone of this theory. It measures the number of steps required to build a biological structure, a numerical value that captures the essence of complexity by quantifying something that is otherwise hard to measure. But how does the standard model of physics fit into this? The standard model of physics. The standard model describes the fundamental particles and forces governing our universe, which seems a world away from the complexities of biology. Yet, assembly theory bridges this gap. In the realm of assembly theory, the standard model provides the foundation for understanding the various forces and interactions. It is the bridge connecting the microscopic world of quarks and leptons with the macroscopic world of living things. Another vital element of this theory is the concept of a state space for a dynamical system, a mathematical concept used to describe all possible states of a system. In the context of assembly theory, this state space allows us to map the path of life's assembly, starting from a single point representing life in its simplest form. The state space continuously expands, branching out into a near infinite realm of possibilities, and each path represents a different course life could have taken. Within this boundless mathematical landscape, the journey of evolution and its complexity unfolds. This mathematical framework offers us a new perspective on the complexity of life. It's not just about the particles and forces described by the standard model, but also about how these elements combine and interact with each other over time, creating the rich and vibrant patterns of life all around us. And it is here that the chaos of random molecular interactions gives way to the order found in the structures of life. So, let's ponder this question. Is the complexity of life merely a product of chance, or is there a deeper reason at play? Let's consider two very different concepts: complexity and entropy. Entropy, a measure of disorder or randomness, seems to be at odds with the complexity we observe in life. In the natural world, how do these opposing forces coexist? This is where assembly theory offers a revolutionary perspective. At the core of assembly theory lies the assembly index, a revolutionary tool designed to measure life's complexity. Picture it as a cosmic ruler, measuring the steps needed to assemble a biological structure from its simplest building blocks. Imagine a single molecule as the starting point on this ruler. As you move up its scale, each step represents a more complex assembly, moving from molecules to cells and on to higher structures. The higher the index, the greater the complexity, and the less likely it is that the structure could have formed by chance. Now, let's delve deeper into the interplay between entropy and complexity. Entropy, a concept from thermodynamics, suggests that systems naturally tend toward a state of disorder. Life, however, seems to defy this trend. From its simple origins, it has evolved into a vast diversity of forms, assembling into the complex and ordered structures we see today. So how does assembly theory resolve this apparent contradiction? It suggests that life, at its core, is a process of overcoming entropy through the lens of the assembly index. We can see that life's complexity isn't a defiance of entropy, but rather a journey that progresses within its flow. Consider the early Earth, a primordial soup teeming with simple molecules over the vast expanse of time. Driven by the laws of physics and chemistry, these molecules began to assemble into more intricate structures. Each step in this journey of life marked a small victory over entropy, a step toward greater complexity. When we rethink evolution from the perspective of assembly theory, we see it not merely as a biological process, but as a kind of mathematical inevitability. The emergence and evolution of life becomes a tale of ever-increasing complexity, a story written in the language of mathematics. Now, let us turn to a question that, while familiar, can be seen in a new light. Are we alone in the universe? For centuries, the search for extraterrestrial life has captured our collective imagination. And now, thanks to assembly theory, we have a new tool in this cosmic quest. Assembly theory provides a unique approach to detecting extraterrestrial life. It isn't about scanning the skies for radio signals or analyzing light spectra for oxygen. Instead, it's about understanding the complexity of molecules and structures that could hint at the presence of life. Imagine using assembly theory to analyze an atmospheric sample from a distant exoplanet or a surface sample from a moon in our solar system, looking for patterns that signify life. The higher the assembly index, the greater the probability that these molecules were created by living processes and not by random chance. However, the path to discovering extraterrestrial life is filled with challenges and limitations. One of the greatest hurdles is our own understanding of what life is. Our definition is based on the life we know here on Earth. What if extraterrestrial life doesn't fit our biochemical criteria? Another challenge is the immense vastness of the universe. The cosmos is so expansive, and our current technology limits our reach. Even with our most advanced telescopes and probes, we can only analyze a minuscule fraction of the cosmos. Moreover, as powerful as assembly theory may be, it is still in its early stages. It's a new method, and its application in the search for alien life remains uncharted territory. There are questions about its applicability and accuracy in environments that are vastly different from our own. Despite these questions, the potential of assembly theory in the search for alien life remains immense. It could redefine our understanding of life in the cosmos, opening new doors for the field of astrobiology. So, assembly theory offers us a new lens through which to view life, not just as a biological phenomenon, but as an emergent property of the universe's complexity. Picture our planet in its infancy, a world in constant motion, a crucible for the chemistry of life. In this chaotic environment, simple molecules embarked on a journey of assembly, a process governed by the laws of physics and chemistry, yet leading to a much deeper outcome. According to assembly theory, life emerges when these molecular structures reach a certain threshold of complexity, one where they can store and replicate information. This is where chemical memory plays a crucial role. It's a pivotal step in the evolutionary process. Chemical memory is the ability of certain molecular structures to preserve their form. In other words, it is life's blueprint. In the world of assembly theory, replicability is key, the ability to copy these patterns and pass them on from one generation to the next. This is the engine that drove life's evolution from the simplest molecules in the primordial soup to the rich diversity we see today. In this evolutionary journey, every step marks an increase in the assembly index. Every gain in complexity represents a victory over the entropy that pervades the universe. But the story of life's origin and evolution is more than just a tale of increasing complexity. It is also a story of resilience and adaptation. Life has found a way to thrive in extreme environments, from the depths of the ocean to the very edge of space. In the realm of scientific discovery, every new theory faces scrutiny and debate. Assembly theory, a concept that promises to revolutionize our understanding of life and complexity, is now at a crossroads, challenged by critics such as Dr. Hector Zenil. The criticisms raised by Zenil pose fundamental questions about the future of assembly theory. His article, at 18,000 words, requires roughly 1 to 2 hours of dedicated reading. This is no mere surface-level glance at the subject, but a deep dive into the heart of scientific debate. For those who are interested, we have linked to both articles in the description, the original study, and the rebuttal. Looking ahead, The role of assembly theory in scientific research remains uncertain. Will it adapt and overcome these challenges, or will it become merely a footnote in the history of science? Despite the disagreements, one thing is clear. The debate around assembly theory has sparked a conversation about the very nature of scientific discovery. It underscores the need for transparency, rigor, and humility in the pursuit of knowledge. Ultimately, the impact of assembly theory on future research may not lie in its specific claims, but rather in the insights it offers us about the scientific process itself. In the quest to unravel the mysteries of life in the cosmos, theories will rise and fall. But the pursuit of understanding, the quest to unlock the enigma of our own existence, will always remain at the heart of scientific inquiry. Supernovae are more than just breathtaking cosmic events. They are essential phenomena that shape and create our universe. These powerful explosions mark the end of a massive star's life cycle, blasting all sorts of elements out into space. From these elements, new stars, planets, and even life itself can form. In essence, supernovae are both the destroyers and the creators of galaxies. In the study of these cosmic events, images play a vital role in helping us understand these powerful explosions. Over the years, advances in imaging technology have enabled astronomers to capture spectacular views of supernovae in various stages, revealing intricate details of their structure and the elements they cast out into space. The story of the red supergiant, Betelgeuse, is a perfect example of how we are coming to understand the behavior of supernovae. Betelgeuse has recently drawn attention for its sudden dimming and brightening. This change in brightness sparked speculation that it was about to explode, capturing widespread interest. In telescopes, a dust cloud observed and photographed around the star was initially thought to be a precursor to a supernova. However, it was later understood to be a natural phenomenon in the life cycle of a red supergiant. So, why did scientists initially assume this star would be the next observed supernova? This red supergiant holds a prominent place in the constellation Orion, resting on its shoulder. It's visible even to the naked eye. Let's look at the life story of Betelgeuse, a fascinating journey that shows the star's evolution from its birth to its current state as a massive, pulsating giant near the end of its life. Betelgeuse began as a massive star, burning hydrogen in its core like many others. However, because of its immense size, it evolved quickly, entering successive stages of nuclear fusion. The star's great mass set its evolutionary path apart from that of smaller stars like our Sun. The Sun is currently a stable, main-sequence star, slowly converting hydrogen into helium. But Betelgeuse, being much more massive, exhausted its hydrogen reserves much faster, evolving into a red supergiant. The key difference between Betelgeuse and the Sun is their mass. Betelgeuse is about 15 to 20 times more massive than the Sun, so its core endures much higher pressure and temperature. This accelerates the process of nuclear fusion. This intense fusion causes Betelgeuse to burn through its fuel rapidly, leading to an unstable structure and significant fluctuations in brightness. In contrast, the Sun's lower mass allows it to remain stable for billions of years with a longer and more steady burning phase. As Betelgeuse aged, it entered successive stages of nuclear fusion, gradually burning elements heavier than hydrogen. The internal pressure caused the star to expand, transforming from a main-sequence star into a red supergiant. This stage is characterized by Betelgeuse's enormous size and its changing brightness. The star expands and contracts as it undergoes complex fusion processes. Recent observations suggest that Betelgeuse might be on the verge of a supernova. The star's dimming in 2019, followed by an unexpected brightening, led scientists to speculate that it might be approaching the final stages of its life. These changes in brightness are thought to be related to internal processes, possibly signaling the beginning of core collapse. Scientists analyzed the star's pulsation periods of 185, 230, 420, and 2,200 days to understand its internal dynamics. Among these, the longest 2,200-day cycle is particularly interesting, as it might represent Betelgeuse's fundamental pulsation mode. indicating it is in a late stage of evolution. These observations, along with recent telescopic findings, suggest that Betelgeuse might be entering the carbon-burning phase right before a supernova. But what complex nuclear process determines that a star's life must come to an end? In the heart of massive stars like Betelgeuse, nuclear fusion converts hydrogen into helium, releasing tremendous energy. As the star ages, heavier and heavier elements are fused, forming a structure like the layers of an onion. Eventually, the core fills with iron, which cannot release energy through fusion. This leads to a gravitational collapse. As the core collapses, it triggers a runaway reaction. During this process, the iron core implodes under immense gravity, with temperatures reaching billions of degrees. This causes a rebound effect. The core expands, and the resulting shockwave tears the star apart. A supernova explosion releases a colossal amount of energy, briefly outshining its entire galaxy. The mechanics of this process involve a complex interplay between core collapse, gravity, and intense heating. The shockwave generated by the core collapse travels outward, ejecting the star's outer layers into space. Ancient astronomers recorded these bright phenomena for thousands of years, sometimes describing them as guest stars or new stars. The earliest recorded supernova observation dates back to 185 AD, when Chinese astronomers observed what they called a guest star. This guest star was visible for 8 months. Although supernovae are rare, astronomers still study them today, especially when they trigger unusual phenomena like gamma-ray bursts. Gamma-ray bursts are powerful flashes of gamma rays, often associated with the collapse of massive stars or the merger of neutron stars. These bursts are among the most violent events in the universe, capable of releasing more energy in just a few seconds than our sun will in its entire 10 billion-year lifetime. The gamma-ray burst detected in October 2022, also known as the brightest of all time, or BOAT, was a milestone in gamma-ray burst observation. Its unprecedented brightness and startling impact on Earth stunned astronomers. The BOAT, officially designated GRB 221,009 amperes, was detected on the 9th of October 2022. It originated from a galaxy about 2.4 billion light-years from Earth. This event was not only exceptionally bright, but also very long, lasting for about 7 minutes, much longer than a typical gamma-ray burst. The energy from this burst was so powerful that it affected Earth's ionosphere, temporarily disrupting radio communications and altering the electrical state of the atmosphere. The relationship between supernovae and gamma-ray bursts is both complex and fascinating. In some cases, the collapse of a massive star's core can trigger a gamma-ray burst, especially if the star is rapidly rotating and has a strong magnetic field. These long gamma-ray bursts usually last more than 2 seconds and are often followed by a supernova explosion. The BOAT gamma-ray burst was not only remarkable for its brightness, but also offered clues about the formation of heavy elements. This past April, scientists conducted a detailed study of the burst, initially hoping it would provide clues to the origin of elements heavier than iron. These elements are typically formed in supernovae or neutron star mergers. However, further analysis showed that this gamma-ray burst did not produce these elements, which only deepened the mystery for scientists and highlighted the enigmatic nature of this cosmic phenomenon. To uncover the true cause of this burst, scientists used multiple instruments, including the James Webb Space Telescope. The burst's extraordinary brightness initially obscured its surroundings, making it difficult to observe an accompanying supernova or other objects in its host galaxy. It wasn't until months later, when the brightness had faded enough, that detailed observations could be made. The results revealed a relatively faint supernova remnant, which was surprising given the immense energy of the gamma-ray burst. The BOAT also gave us a deeper understanding of the characteristics of gamma-ray bursts. The event's unusual brightness and long duration suggest that the energy of the burst was highly focused, with a narrow jet pointing directly at Earth. This narrow beam might be the reason for its observed intensity, as gamma-ray bursts tend to be directional phenomena. The narrow jet was likely caused by a powerful and focused explosion, produced by a rapidly rotating star with a strong magnetic field. Although the boat has helped our understanding of gamma-ray bursts and supernovae, scientists are still working to find answers to the mysteries of Betelgeuse. Recent studies suggest that the cycles of Betelgeuse's brightness are part of its natural behavior as a variable star. It turns out that, unlike the Sun, Betelgeuse is an extremely unstable and low-density cloud of plasma, constantly changing its shape. Scientists' simulations have shown Betelgeuse's behavior during its brightness changes, which occur roughly every 400 days, with a longer cycle of about 2,000 days. Recent research has tried to explain the Great Dimming event that occurred in 2020. Observations from various telescopes over the past 15 years have provided many insights. Observations at different frequencies, including microwave and infrared, allowed scientists to peer through Betelgeuse's outer layers and detect silicon monoxide, which indicated the presence of a massive dust cloud. This discovery overturned the initial speculation that Betelgeuse was about to explode. Instead, it seems the star activity deep within the star caused it to shed material, forming a vast cloud of gas just beneath it. A cool patch formed, causing particles to condense into a dark cloud that obscured our view of Betelgeuse from Earth. Further studies of Betelgeuse's behavior revealed that the star experienced two shock waves, one in 2018 and another a year later. These shock waves roiled the star's surface, creating both hot and cool spots. This phenomenon was confirmed by ultraviolet observations from the Hubble Space Telescope. These shock waves and their aftermath dispelled the initial theory that Betelgeuse was about to go supernova, suggesting instead that this behavior is a natural part of the star's life cycle. This is also evident in its rapid rotation. Unlike a typical, slow-spinning red supergiant, Betelgeuse turns at a speed of about 3 meters per second. This initially led researchers to believe it might be the result of a collision between two stars, but more recent studies suggest that this rotational speed may be influenced by rapidly moving convection cells deep within the star. This contradicts the initial assumptions about its spin, and while the behavior of Betelgeuse is certainly unusual, this research suggests it is unlikely to go supernova within our lifetimes. The star's current state is more like that of a variable red supergiant nearing the end of its life, but it is still far from a supernova explosion. Now, let's explore a question that concerns us all. What kind of impact would such an explosion have on our home planet? The potential effects of a nearby supernova on Earth is a topic filled with speculation and concern. While a supernova isn't expected to pose a direct threat to our home, a stellar explosion within tens of light years of Earth could affect our planet's atmosphere and potentially impact life. For example, one gamma-ray burst was so intense that it significantly affected Earth's ionosphere, changing atmospheric conditions and disrupting radio communications. This burst released enormous energy that interacted with Earth's atmosphere, causing a sudden increase in electrical conductivity. This increased conductivity affected the ozone layer and triggered chemical reactions that scientists are still working to understand. The gamma-ray burst also interfered with radio signals, especially those used for communication and navigation. The energy released by the explosion was so immense that it even blinded several satellites, demonstrating the immense power of these cosmic phenomena. However, this burst was observed in a galaxy 2.4 billion light-years from Earth. This event highlights the need for further research into gamma-ray bursts to understand their impact on us, our planet, and the universe as a whole. Furthermore, supernova research also helps us understand dark matter, dark energy, and the overall structure of the universe. Type Ia supernovae, which occur in binary star systems, are crucial for measuring cosmic distances and studying the expansion of the universe. These standard candles helped astronomers discover the accelerating expansion of the universe, which in turn provided the context for understanding dark energy. Supernovae are a key focus of future astronomical research. Their explosive nature and transformative impact continue to fascinate scientists and inspire new discoveries, while some people on internet live streams eagerly await the explosion of Betelgeuse. We look forward to the new discoveries that missions like the Vera C. Rubin Observatory and the European Space Agency's Euclid telescope are expected to bring. These will help advance our understanding of supernovae. As our exploration of the cosmos deepens, these stellar explosions will undoubtedly shape our understanding of the universe and our place within it.